Alright guys, welcome to our unit on quadratic functions. This is the very first lesson here. In your books you should definitely go over and read the unit overview, the key terms. Here's some academic vocabulary, and actually while I'm doing that, let me just get my commenter out. And we have a bunch of different math terms as well here. Hang on a second. Okay, quadratic equation, standard form of a quadratic equation, imaginary numbers, complex complex conjugate, completing the square, discriminant, root, zero, parabola, focus, directrix, axis of symmetry, vertex, quadratic regression, and vertex form. All of those math terms you will become very, very familiar with. Okay. So as far as getting ready goes, we did this in the beginning of class. I do want you guys to make sure that you can do all of these, factoring these expressions first of all. We will get a lot more practice with factoring, but and then also just graphing these different things here. Okay, this is an equation of a line. Here we've got another line with our x-intercept, given the x-intercept and y-intercept, and then graphing the parent function for an absolute value, and then some transformations on that, and then finally solving this equation here, this quadratic equation for x squared minus 3x minus 5 is equal to 0. All right, but anyway, let's go ahead and I guess we'll go through these pretty quickly. I'm not going to go over how to factor some of these because some of you have learned different methods on how to factor these, but I'm going to just kind of go through my method. Anyway, so the first one is just pulling out a GCF, which is the opposite of distributing. When we distribute, you'd have like something on the outside of here, and then you'd multiply in, right? With a GCF, you're taking out a greatest common factor, just like what we're going to do here in a second. What am I going to pull out of here? So, and again, that would look like this. If you have parentheses, both of these terms, okay, they have a 6 and a 12, all right, and I could pull a 6 out, all right, so divide both of these, by 6, and then just listing what's left over on the inside. So, and you guys should already have done this, plenty of this before. But anyway, so I'm going to pull out a 6. Right? I'm going to pull out between an x cubed and an x squared, I can pull out the x squared. Between a y and a y squared, I can pull out the y. And when I pulled out that greatest common factor, if I pull out the 6 in the first one, I'm just left with 1. If I pull out an x squared, I'm left with an x. And if I pull out a y, then I'm just left with that y there. Or I'm sorry, left with 1. So it's just x in this case. And then plus, and then if I pull out a 6, I'm left with 2 because I have 2 6s going to 12. And if I pull out an x squared, that's just 1. And if I pull out a y, then I'm left with y. Okay. So the greatest common factor would be 6x squared y, and we just pulled that out of both of these. Okay, so as you can see, it's the opposite of distributing. If I multiplied this back in, then I would end up back with what I originally had. Next one up here, I'm looking for to factor this thing, and so this is going to be equal to, and this is x, and because this is an x squared here. And what I'm looking for are two numbers that add to get positive 3 and multiply to get to negative 40. And those two numbers are positive 8 and negative 5. All right. Now, again, positive 8 plus negative 5 will give you positive 3, and positive 8 multiplied by negative 5 will give you negative 40. And if you multiply this back out, then you would end up back with that that expression. This is known as a difference of squares. I have one square minus another square, and so you can always just do this where you have plus and minus, and you just take the square root of the first one and then the square root of the second one. So square root of x squared is x, and the square root of 49 is 7. So you end up with x plus 7, x minus 7. Difference of squares. And then finally, the last one I'm going to do the same as number 2. And so this is going to be equal to x and x. And two numbers that multiply to get positive 9 and add to get to negative 6 would be negative 3 and negative 3. Okay. And I'm going to graph this guy right here. So y-intercept would be negative 3 halves, or negative 1.5. So right here. And the rise over run, the slope is 3 over 4. So 1, 2, 3, 1, 2, 3, 4. Here's my next point. 1, 2, 3, 1, 2, 3, 4. And go down 1, 2, 3, 1, 2, 3, 4. And one more 1, 2, 3, 1, 2, 3, 4. And we'll go ahead and connect these dots. And that gives us our line. All right, number 6. So actually, let me zoom in here. See how that looks. Okay. Oop, something. Don't know what that is. Hang on one second. Let me just zoom back out. It's kind of weird. All right. Anyway, okay. So graph a line that has an x-intercept. So where does it cross the x-axis at 5? This really should be a point 5, 0, 5, comma 0. And a y-intercept of negative 2, which would be where does it cross the y-intercept? That should be 0, comma negative 2. Right here. And go ahead and draw your line. Okay, and there you go. That's it. Next up, number 7, we'll graph the absolute value of x, which has a vertex as the parent graph at 0, 0, and it just goes up like that, and over here like this as well. That gives you this V shape. Okay, and this guy right here, x plus 3, let's use a different color here. So this guy right here is going to shift to the left 3. So the vertex goes 1, 2, 3 over. And there are no other transformations, so it just goes like that. And like so. And then we'll choose one more color for this guy. Let's do purple. For the absolute value of x plus 3, this goes up 3. 1, 2, 3. And this actually should be on the same line as this, if I was able to draw these perfectly. So anyway, all right, and then finally we're gonna solve this quadratic equation here. So the first step is to factor this thing. So two numbers that multiply to get to negative 5, and then add to get to negative 3, and in this case that does not exist. Okay, so there's really only one way to solve this, and that's to use the quadratic equation. So if you recall, the quadratic equation is the opposite of b, so x is equal to the opposite of b, so like that, plus or minus square root of b squared minus 4 times a times c, all over 2a. And that's when you're given the equation in standard form of ax squared plus bx plus c is equal to 0. Okay, so let's go ahead and plug these coefficients in here, because we have a 1 in front of here. We got negative for a, we got negative 3 for b, and negative 5 for c. All right, so x is equal to the opposite of b. So we got negative 3 plus or minus the square root of negative 3 squared minus 4 times a, which is 1, times c, which is negative 5, all over 2a, or 2 times 1. And we'll simplify this a little bit to get 3 plus or minus, and this would be 9, negative 3 times negative 3, negative 3 squared is 9, plus 20, in this case, negative 4 times negative 5 is 20, so we have the square root of 29 all over 2. And yeah, you can pretty much leave it there, actually. This would be considered an exact answer. Actually, two answers. We have the plus version and the minus version. Um, if you want to know the decimals, you'd actually calculate this out, but typically we want these in the most simplified version possible, which this would be because it is exact. All right, so let's get to the lesson. Those are all things that you should already know. All right, so lesson one is analyzing a quadratic function. And I'm going to kind of fly through this a little bit here. And I just want to note a couple of different things. First of all, what's a quadratic equation? What makes a quadratic equation? Well, first of all, a quadratic equation is any polynomial equation that has the highest exponent of x squared. Okay, so we'll say highest exponent equals 2. For example, I could dream up some crazy, stuff here. I guess I can't get that crazy, but for example, if I had y is equal to x squared minus 5x plus 1, because the highest exponent for x is 2, and x squared, that's what makes it a quadratic equation. Notice that this is actually x to the first power, and technically speaking, this would be x to the 0 power term, because x to the 0 is just 1. So you kind of go down the line, okay? X squared minus 5x to the first plus 1 times x to the 0. You just have to be aware that this term does exist. It'll become important later on. Anyway, so highest exponent is 2. Number 2, I guess, just to summarize some of the major points for quadratics, is it revolves around the graph, really. So, for example, these graphs are always going to be parabolic. Okay, so maybe something like this, maybe something like this. Okay, doesn't matter really where they are, how wide they are. It's going to be some kind of parabola. And when we answer these questions, most of the time, we are really interested in only a few points here, which would be like the maximum and minimum. So this has a maximum, this parabola right here has a maximum right there. This one has a minimum right there. We're also interested in where does it cross the x-axis, okay? These are primarily the 3 points, actually, that we are mostly interested in, okay, when we're answering these questions. So just to give you a heads up, even though these things go on forever in this direction, and this goes on forever in that direction, we're primarily just interested in max and mins and where does it cross the x-axis. By the way, this one over here would never cross the x-axis, okay? And that's where we're going to get into imaginary numbers and complex numbers, which is just how we write our imaginary numbers. Okay, so without further ado, let's go through the actual lesson. And this is really kind of just an exploration. But I will say this. This has to do with the question on the SAT that our high school got wrong the most. Or we scored the lowest, I should say, on the SAT. And this has to do with like a simple question like this. Let me just put the question over here. Say, for example, you have a, well, we're going to go over this in a second, but I think they used a picture frame on the SAT. But basically, you've got area in here, and if they give you the area, say like, I don't know, 500 square whatever units, whatever that happens to be, and they give you like one of the sides is, I don't know, the length, and the other one is like 20. What is the expression used in order to, or the equation used in order to solve this problem? Now, this is obviously pretty easy to solve, but the equation, and actually it's pretty easy to come up with the equation too, but for whatever reason, this happens to be one of the more difficult problems, or the problem that our students have issues with the most. Okay, so so basically our first couple of examples here go through that. So for example, we've got 100 feet of fencing, all right, to enclose the largest possible rectangular area, but we've got 100 feet. All right, and we're going to find the width of the rectangular enclosure. I'm sorry, if the width is 20 feet, what must be the length? Well, okay, let's draw a little picture here. So here we've got length. We'll call that length here and width here. So if the width is 20 feet, that means that this is also 20 feet, right? So we only have 100 feet available to us, 100 feet here. Okay, and if this is 20 and this is 20, that's 40 total. So we only have 60 left. So what must be the lengths of the, what must be the length? Well, it must be 60 divided by 2, which is equal to 30. All right, so we would say 30 feet. Okay, so if this is the case, we're going to choose several values for the width of a rectangle with a perimeter of 100 feet, and we're going to determine the corresponding length. So for example, say our width was only like 1 foot. Okay, well, that's 1 on each side, right? So that's 2 feet. Remember, we have 100 feet total. That's 2 feet. So now I have 98 feet left, and well, what's 98 divided by 2? Well, the length must be 49 feet. And what's the area? Well, it's just width times height, or width times length, which would be 49. All right, so let's change this up a little bit. Let's do like 5 feet. So if we have 5 feet, then the length must be 45 feet, okay? Because we have 5 times 2 for each of the width sides, so it's 10. All right, which gives us 90 feet left to work with, and 90 divided by 2 is 45. And let's just calculate this out here. 5 times 45 is equal to 225. Let's keep going up. We'll say 10. This must be 40. All right, and so 10 times 40 is 400. Let's do, I don't know, 20. All right, then this must be 30. And 20 times 30 would be 600. Let's go up to 25. Okay, and that means this must be 25. Width is 25, length must be 25. 25 times 25 should be 625. Let me just check and make sure that's all good. Yes, it is. All right, let's keep going up here. Let's go to like 30, for example. All right, going up to from 25 to 30. Well, how much is left here? Well, there's only 20 feet for each side, and 20 times 30 is 600. But wait a second. If we look up above here, we already have 20 and 30, don't we? So now we're kind of just going in the opposite direction. All right, so for example, if I had 40, then that would be 10, and I've already done that. That's 400 right here. So we have 400. And then going back down, let's go all the way down to 49, I guess. 49, 1 is 49. All right, so as we look at this, I just want you to notice that we start low, and then we go up, 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 up. So it seems like we hit some kind of maximum here. And then we went down, 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 down. Okay? And we're going to see what that looks like in a second. It's basically going to correspond to a parabolic shape. If you have an XY axis, like such, then you have this parabola. Okay? So, anyway. We'll get the exact graph of that in a second. So what is the relationship between the length and width of the rectangle with perimeter 100 feet? Well, if you notice, I'm sure you notice this pattern really quickly, but the width plus the length must equal 50. So W plus L is equal to 50. And where did that come from, by the way? I mean, we notice this pattern. Well, it comes from this. We have, for the width, as in our little drawing up here, the width is 2 times the width, right? And the length is 2 times the length. And we have 100 feet total. So it's actually 2 times the width plus 2 times the length is equal to 100. And notice all of these are divisible by 2. And then you would get back to just W plus L is equal to 50. That's how we got that. Okay, so based on our observations, predict if it is possible for a rectangle with perimeter 100 feet to have each of these following areas. Explain this one here, 400 feet squared. I would say absolutely. That's actually one of ours, right? 10 by 40 here. We would say yes. And so let's just say 10 by 40. 500 feet, well, again, we'll say yes. And why is that the case? Well, I mean, we're going from 49. We're just picking arbitrary numbers here, but we go all the way up to 625. So you know, it leads us to believe we could definitely pick some kind of width and height or width and length and to get 500, but it might be decimals or something. Yes, but might be weird numbers. Oops. Yes, but might be. Sorry, this is kind of sloppy. Yes, but might be decimals. Kind of sloppy. It's really sloppy. Anyway, let's go down to 700. Well, as we saw here, the maximum as far as we can tell is 625. You know, we'll see that for sure in a second here, but no, we'll say no. Max appears to be 625 feet squared. All right, and so now let's get to the meat of this. This is actually the part where most of our students were not able to put this together on last year's SAT. So number 5 says, let L represent the length of a rectangle with perimeter 100 feet and write an expression for the width of the rectangle in terms of L. Well, we already said that width plus length must be 50. All right, so again, if L represents length, which it does right here, if we want to express this in terms of W, right, and for width in terms of L, we're going to express it for W in terms of L, then that would just be W is equal to 50 minus L, right, just moving this L over. All right, and then here we go. This is this would be the answer, for example, to that type of SAT question. So number 6, express the area A of L for a rectangle with perimeter 100 feet as a function of its length L. Well, how do we figure out the area of this thing? Well, we simply took the width times the length. So, but what is the width? The width is 50. Hang on, let me make this a little bit better here. The width, all right, was 50 minus L times the length, which is just L, okay, and that's it. There's your expression, or your equation, actually. All right, so anyway, so let's go ahead and graph this thing. Okay, now I don't have, again, TI-83, you know, the whole software thing installed on this computer. So what I am going to do is I'm going to graph it, or I did graph it actually, on what's called Algebra. And not this one. Let me see, where is this? Cross that out. Okay, so here we are right here, and actually this one is not the correct one. This would be a different one that's coming up. Let me just change this. So this is 50 minus x, so hit enter here. All right, and let me go ahead and move this down. All right, so this is kind of narrow, but that's okay. So one thing I want you to notice is that I put a slider in here, which basically it just shows us what it's not what A. There's probably a bad name for that. Let me see if I can change the name of this real quick. Let's just call this I don't know if I can call it something different. Let's see, or something complicated, I should say. Can I say intersect? Let's see if that'll work. Oh, it does work. Okay, because that's all I really want here is I'm just kind of moving this line going across the X and then just figuring out where it crosses it, where that intersection point is, as you can see. Okay. Anyway, so this thing starts at 0, 0, and the highest point is going to be at exactly, let's see if I can get this right. Oh, it's too... do the settings for this. Hang on. Let's do increments of 1. Go up to 50. Did that work? Nope. Let's try it over here. Hit enter. Okay, there we go. All right, so now, yeah, there we go. That's much better. All right, so at 25, A is 25. The intersection is at 625, and you can see if we zoom in here, all right, that's the peak of this thing, the maximum. Okay, so, but anyway, let's go ahead and draw this with those points, and you could go ahead and draw it with the points from your table, but again, not really that necessary to get too crazy with this. So we're going to start at 0, 0, and by the way, this thing is going to go to 50, 0. All right, and the highest point is going to be 625 at 25 right here. Okay. And just remember at 10 it was 400, so I'm going to try to put some of these in here. At 40 it was also 400. Let me actually grab some of those points because it's nice to have more points on here. At 545 it was 225, so 225 right here, and at 45 it would be 225 as well. This thing is symmetric. At 2030, it was at 600. At 30, 20, 600. All right, so let's go ahead and connect these dots here. Do the best I can. Oop, get a little wobbly at the end there. Okay, now technically this thing goes on forever down each way. Okay, but since this is a real life problem, we're actually going to stop it at 0 and 50. And also, technically speaking, a student had a really good question about this today. Technically speaking, it couldn't actually be 0, and it couldn't actually be 50. All right, if the length was 50, okay, there would be no more room for height. So it would just be, or width, so it would just be a straight line or a segment. Okay, but could it be 0.000001? Well, yeah, it could be. Okay, so basically goes all the way up to those points, not including them. Okay, so there's the graph of our quadratic function, which represents the area of all the possible solutions for you to have the lengths of a rectangular area of but it has to add up. The perimeter has to add up to 100. All right. Let's see here. This is talking about, setting up your window, corresponding values and axes. So basically, and again, I apologize, I don't have this up here, but you do want to become very familiar with your calculator and setting the window. So you could click on window, which is at the very top, one of those top functions there, right next to y equals. And you could set the x min to be 0, x max to be 50, and you could set the y min to be 0 and the y max to be 625, and you would see this segment, the one that we want of this particular object, which is a parabola. Okay. You could also do a lot of other things, like you can hit the trace button and you can kind of trace along here and see what the values are. You can do second calc. Okay, second calc brings up a lot of different things. You can calculate a value at a specific x. You can find the zeros, or the roots. You can find the minimum and maximum by just putting in some boundaries. You can find the intersection of different graphs as well. Okay, different functions. And there's a couple calculations there, which would be the derivative and integrals. But anyway, that's all in the calc, which is right above trace, by the way. You could also go to the table, which is right above graph, and check out the XY values. Okay, I would encourage you to play around with that. Now, if you ever want to reset your window, just hit zoom, and then 6 is Z standard. Okay, 6 is Z standard. You could also go to zoom, and where's my zoom at? I have it down here, even though you guys can't see it. There's also, if you go down to 0, it's zoom fits, and it will actually do its best job at fitting whatever you're trying to graph into the window. Okay, so all kinds of ways to just kind of reset that. All right, let's see here. What is the reasonable domain? And remember, the big thing here is going to be reasonable. domain of the function in this situation. So in this situation, because parabolas go on forever, right? But this is a particular situation, and it couldn't go down to 0 or be negative because you couldn't have a negative width or length, okay? So the domain would go from 0, okay, all the way to 50. All right. Let's see here. So let's go ahead and put that in here. So the domain, oh, it does say that it wants us to express it as an inequality, interval notation, and set notation. So let's do all of these. So domain, that would be from 0 to 50, so as an inequality. And this is actually length on the x, not x itself, so length. And it can't be 50 as well. Okay. And then if we want it as an interval, it would go from 0 to 50. We're using parentheses because that's not included. And then as set notation, okay, this is the fun one, right? The set of L such that L is an element of the real numbers, because we want to include everything, even the decimals and all that stuff. And L will be between 0 and 50, like so, and then close your brackets, your curly brackets, curly brace. Anyway, over what interval is of the domain is the value of the function increasing? Okay, this is very interesting. And where is it decreasing? Well, let's go back up here. So what does it mean to be increasing? That means going up. All right, and a little foreshadowing here. You're very interested in this question in calculus and how you measure it, because sometimes it can be difficult. It's pretty obvious to us that it's going up and up and up and up and up until it hits this guy right here at x is equal to 25, and then it goes down, 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 down. Sometimes it's not so obvious. In calculus, what you do is you actually will pick a point and you come up with the line that is tangent to that point, where it intersects this curve only at one point. And as long as the slope of that line is positive, it must be increasing at that point, right? At this point here at the very top, the tangent line would be exactly horizontal, so it would not be positive. It's 0, right? So it would no longer be increasing at that point. After that, once you start going down, the slope of the little tangent line starts becoming negative, okay? So anyway, just a preview for calculus for those of you who end up taking calculus, okay? But either way, it is increasing from 0 all the way up to x is equal to 25, okay? Up to that point. This whole thing here is increasing. Okay, not including 25, because at 25 it would actually be 0, which is neither increasing nor decreasing. So anyway, so let's go ahead and write that down. So what interval is it increasing? So we'll say increasing, and that's going to be from between 0 and 25. As an interval, that would be 0 to 25. And set builder, oh, they don't actually tell us to do all that, but that's okay. We'll do it real quick. The set of L such that L is an element of all the real numbers, and L is between 0 and 25. And for decreasing, do the same thing. It's between 25 and 50. And the interval will be 25 to 50, not including, and then the set of L such that L is an element of all the real numbers, and, oops, not 0. L is between 25 and 50. And close your set. All right, what is the maximum rectangular area that can be enclosed by this 100 feet of fencing? Well, and we just said how, we said where is it increasing, where is it decreasing? Well, what's in between where it's increasing, decreasing, where L is 25? So what is the maximum rectangular area? Well, that would be 25 times 25, which would be 625 feet squared. and we'll say where L is equal to 25 and W width is equal to 25. In particular, this creates a square, which is important. If you have complete flexibility to change all sides, then a square will always give you the biggest area. But we're going to have a lot of problems where you're not going to be able to change like one side or two sides, or maybe it's not even going to be a square or a rectangle. Maybe it's going to be like, you know, some kind of diagonal in there, diagonal fence or whatever. So anyway, but if you have complete flexibility, it's always a square. Anyway, so what is the reasonable range for A of L in this situation? In other words, the area. So what's the lowest the area can be? Well, I already told you that if it was, let's go up here. If it was like 0, actually, let's go back up all the way to the top. Let's start with this one, 149. So you might first think, well, if the width was 1 and the length was 49, then the lowest would be 49, right? But then you're thinking, oh, wait a second. What if the width is less than 1 foot? What if it's like 0.01? Right? We could do that, and it would start minimizing this area and get smaller and smaller and smaller. What if the width was 0.000001? Then the length would be 49.9999999, and it would get closer and closer and approach 0. But it could never actually be 0 because we could never have a width or length of 0. It has to be something bigger than 0. So, going back down here, what is the reasonable range of A of L in this situation? Well, it could go from 0 up to, but not including, we'll just say A for area, but not including 0, okay? And it could go up to, as we said, well, 25 by 25 could be 625, and that is including that value. 25 by 25 would be 625 square feet. Again, interval notation will be from 0, not including, up to 625 inclusive, so we have a square bracket. And then finally, set builder, we've got A, the set of A such that A is an element of all the real numbers, again, because it could be decimals and all kinds of stuff, where A is between 0, not including 0, and 625 inclusive. Like so. Let's see, how did your answer in item 10 help you determine what was 10? Well, we said that, you know, the largest area would be 625. Anyway, let's see here, revise and confirm. I don't think it's really necessary. We've gone through these extensively. You know, like how could this be 400 feet squared? Well, obviously we know like between 0 and 625, 400's in there, right? So it's 500. 700 is not. It's outside of that range, so it's not possible. Let's see here. What are the length and width of the largest rectangular area? That can be, yeah, so if it was 625, we talked about this, right? Its length is equal to 25, and width is equal to 25. All right, and then the length you gave is, in item 13, is the solution of a quadratic equation in terms of L. Write this equation, explain how you arrived at this equation. Well, we've already got that quadratic. It looks like this, so let's do that. So we have A of L is equal to the length times the width, and the width in this case happens to be 50 minus the length, which is equal to 50L minus L squared if I distributed this L, which makes this a quadratic equation. All right, so that's it for the lesson. It was a very long video. I apologize for that. I am going to, actually, you know what, I'm going to do the check your understanding. So, sorry, I'm going to make it a little bit longer. Just a few minutes here. Explain why the function A of L that you used in this lesson is a quadratic function. Well, we already just did that. It has an exponent of 2, highest exponent of 2. So we'll say highest exponent of 2. That's what makes it a quadratic. By the way, if the highest exponent was a 1, then it would be linear. All right, that would be y equals mx plus b, x to the first power. If it had a highest exponent of 3, it would be a cubic function. 4 would be quartic, 5 would be quintic, and so on and so forth. Anyway, how does the graph of the quadratic function differ from the graph of a linear function? Okay, well, obviously a linear function is a straight line, and this has a curve, a smooth curve to it. Also, a line goes, like for example, if a line was going up like this, right? It goes up and down forever. All right, one side will go down forever, the other side will go up forever. Parabola is different though. It's either going to go down forever and have this maximum, or if it looked like this, where it was going upwards, it would go up forever and have this minimum here. Okay, just depends. I think that might even be one of the other questions. Can the range of a quadratic function be all real numbers? Explain, and the answer to that is no. Like we just said, must have a max or min. Not mine, min. Hang on. Max or min, which is not negative, positive, or negative infinity. Okay. It will go to negative, positive infinity the other direction, though. All right, explain how you could solve the quadratic equation x squared plus 2x is equal to 3 by graphing the function f of x is equal to x squared plus 2x. Well, in this case, if you had x squared plus 2x is equal to 3, that means that y must be equal to 3, right? Because you would say y is equal to, just like this, y is equal to x squared plus 2x, and in this case y is equal to 3. So you're just looking for wherever x values give you where y is equal to 3. Okay. All right, and that is all for this lesson. Very long. Sorry about that. And I'll do a separate video on the practice.